All right, so we're going to solve for k here in the following geometric sequence, although we don't know what any of the actual numbers of the sequence are. We just stuck with these algebraic expressions. And what we're going to do is figure out the ratio here. Since it's geometric, we know there's a ratio that's maintained. And what I mean by that, I'll make up another problem with easier numbers, 5, 10, 20. It's easy to see that this is a doubling. But the way you would show that is to say the ratio here, 10 divided by 5, is the same as the ratio between these pairs, 20 divided by 10. These ratios are equal. We're going to use this logic to solve for the problem here, except now we don't have numbers, but we've got these expressions with k. First off, the ratio between these two, if we take 2k plus 3 and divide by 2k, that ratio is going to be the same as this one, 14k plus 3 divided by 2k plus 3. All right, these have to be equal. We're going to solve for k. Now, when solving this, these 3's do not cancel out. You cannot subtract the amount of k's. You can't cancel out these 2k's. As much as we really wish we could do that, that is not how fractions work. Think about a problem like this. If you had 2 plus 3 and you were dividing by 2, it is not true that these 2's cancel. So that is a false statement. Do not do that. And that occurs every time that there's addition or subtraction in either the numerator or denominator. You should avoid this as a strategy. It's not right. So without being able to just willy-nilly cancel out some of the things we wish we could, what we're going to do is cross multiply. Now, I'm going to do this in a couple steps, but if you know how to cross multiply, you can kind of roll things into one. So first off, let's start here. Let's get rid of this 2k. We don't want that in the bottom of a fraction. In fact, we don't want any part of this to be a fraction. So if we multiply 2k over 1, the 2k on the top are multiplying, but then later we're going to divide, and so those factors cancel each other out. To keep it balanced as algebra, we have to do it to the other side, and that's a little messier. In this case, the 2k is multiplying the 3 and the 14k, and the 1 is multiplying the denominator, so it will not change the denominator. If I rewrite what that looks like, 2k plus 3 is the only thing over here. It looks very good. But over here, not so good. This would be 28k squared plus 6k being divided by 2k plus 3. Okay, from here, same strategy. We want to get rid of the denominator, and that represents a division using the opposite operation, i.e. multiplication over 1. This factor and this factor will cancel each other out. Now, to maintain equality, we'll have to multiply over here, 2k plus 3. And now we have two binomials being multiplied. This requires us to do the box method or to FOIL this. So I'm going to start on the right-hand side. That part's a lot easier. It's 28k squared plus 6k, and everything else canceled out, so that's what's left. Over here, if we just do a little side calculation, box method, 2k plus 3, 2k plus 3, that would be 4k squared. This would be 6k, so with this, it's 12k total, and then 9 is in the corner. Okay, so we are left with a quadratic. We know this because there is one term that is squared and one term with regular k, and then we're left with the number 9. In order to solve this, we need to get everything on the same side equal to 0. And if we subtract 4k, we're going to subtract 4k squared. Okay, that will cancel out. we're going to subtract 12k and subtract 9. Nothing to subtract it from, so we just leave it as minus 9. And that's a quadratic. We can take that straight to the quadratic formula, but I always like to make my numbers easier. I'm noticing here that there's a greatest common factor to all of these of 3. And so we can divide both sides by 3, which will not change the 0. It's kind of nice. This becomes easier. 8k squared minus 2k minus 3. So a in our quadratic formula equals 8, b equals -2, and c equals -3. I'm going to take those numbers into the quadratic formula. I'm not going to write that out. I'm going to do that on the sidelines here and come back. Okay, after working that out, there are in fact two solutions. K is 0.75 or k equals -0.5. And one of these might be a bogus answer. Let's test them both. If we go back up here and we put in k is 0.75, that would mean that the first number in the sequence is 1. So if k equals 0.75, 1.5 rather, and then if we put that same 0.75 here, that would then make 4.5, which is multiplying by 3. And the last one here, there, that would be 10 times 7.5, 10.5 plus 3, 13.5. And that is another multiplied by 3. So in this case, we're multiplying 3 each time. All right, so that happened if we plugged in 0.75 as the k value. Let's just double check. What if we put in k is -0.5? And what sequence would that produce? So if this is instead -0.5, that would be -1, -0.5, be 2, -half of that's -7 plus 3, -4. Okay, so in the second instance, it also produces a geometric pattern, although alternating, but that's okay. We're multiplying by -2, and then again -2. So we have two separate options. Both are considered correct, unless somehow the problem had otherwise said strictly the positive version, then we would stick to the positive answer.